Standpipe is basically just this vertical pipe that we attach to some other fluid system, usually a horizontal flow pipe that water is, or whatever fluid is flowing through. So we've got moving water in here. But as the water flows, water is going to rise up into the standpipe. And this happens almost immediately. Like as soon as water starts flowing in the standpipe, in the flow pipe, water rapidly rises up in the standpipe to a certain level and then just stays there. And the reason it flows up only to a certain level and then stays there, let's just call that height H. What do we know about what's going on at the top surface here?
It's an atmospheric pressure.
Yeah, this is going to be atmospheric pressure. I'm going to call this point T for top. And the pressure at point T is atmospheric pressure, which we could call 101.3 kilopascals in terms of absolute pressure. Or what would that be in terms of gauge pressure? What would be the pressure of atmosphere if we're talking about gauge pressure? Do you remember how those quantities are related, the absolute pressure versus the gauge pressure? Because this is an important distinction. If we have these two different ways of describing how much pressure there is. The absolute pressure is supposed to be describing how much pressure there actually is, the actual pressure at that point. But what does gauge pressure mean?
Is it like atmospheric pressure minus the below pressure? So would it be like 0 because it's...
Yeah, exactly. Because the gauge pressure is absolute pressure minus atmospheric pressure. Or to put it another way, absolute pressure is gauge pressure plus the atmospheric pressure. Because atmospheric pressure is basically just a convenient reference point. If you take the atmospheric pressure and subtract 1 atmosphere, you get the gauge pressure, which in this case would be 0. So gauge pressure basically just means we're calling the atmosphere 0 and then measuring everything relative to that. Because in most cases, we don't really care how much pressure there actually is. We just care about differences in pressure. So in gauge pressure, we're describing the atmosphere as 0 kilopascals. And then if we say something has a pressure of like 10 kilopascals, that just means 10 kilopascals more than the atmosphere. Or in gauge pressure, we could even describe pressures as negative. If we say that the gauge pressure is negative 50 kilopascals, that just means 50 kilopascals below atmospheric pressure. But 0 is the gauge pressure, just means the same as the atmosphere. Any positive value for gauge pressure means higher than the atmospheric pressure. Any negative value means less pressure than the atmosphere. Absolute pressure, on the other hand, tells you what the pressure actually is. And you can't have a negative absolute pressure because 0 absolute pressure means no actual pressure at all, like a complete vacuum. The reason we call this gauge pressure, though, is that we typically measure pressures relative to the atmosphere anyway. If you are using like a pressure gauge on a bicycle tire, you're not actually measuring the pressure in the tire. You're measuring how different that pressure is from the surrounding air. So all pressure gauges are really just measuring pressure differences anyway. But let's compare this point on the top, which we could call 1 atmosphere of pressure as an absolute pressure, or we could call it 0 as a gauge pressure. Let's compare that to the bottom. Let's call this point 1. If we're comparing point T and point 1 using a Bernoulli equation, let's see what the... So Bernoulli equation, and we could subtract, for all the deltas, we could subtract T minus 1, or we could subtract 1 minus T. It doesn't really matter as long as we're consistent about it. We're presumably trying to find the pressure at point 1 though. So let's call these deltas 1 minus T. That way, if we're trying to solve for, like for instance, delta pressure is going to be P1 minus PT, and then we can just add PT to both sides. So if we're comparing 1 and 2, first of all, the only reason we're allowed to do that at all is if we draw a path from 1 to 2, or 1 to T, what fluid system is that passing through? What fluids are involved here? Yeah, we've got water, although this actually counts as 2 fluid systems because what's this water doing?
Flowing.
Right, this water is flowing, and this water up here?
It's stagnant.
Right, that's stagnant, that's stationary, just staying still. When we first turn it on, the water starts to rise up, but as soon as it reaches some equilibrium level, it just stays there. So the water in the standpipe, once it reaches equilibrium, is not moving. And it's also not mixing with the flowing water in a significant way. In fact, this doesn't even have to be water. You could have like a column of oil balanced on top of the flowing water, and it could just stay there, not mixing with the flowing water at all. So we've got to be careful here. Formally, we're going to put point 1 on the border between the flowing water and the moving water. If we put it on the border, then it counts as a part of both systems at once, the flowing water and the moving water. So that this path is only traveling through stationary water. But since point 1 is on the border, the pressure at point 1 is also the pressure of the flowing water at that point. So if we're looking at from point 1 to point T, what are the only types of energy density that are changing? What are the only terms we need in that Bernoulli equation?
Potential energy.
Yeah, there's definitely a change in height and therefore a change in potential energy. So I'm going to call that rho g delta y. I'm going to use y here because we're already using h to represent the height of the tube, like how high the water goes. So we'll just use y to represent different locations. And what else could be different between points 1 and point T? Yeah, they're going to be at different pressures. We know point T is at atmospheric pressure, which again, we could call 0 or 101.3 kilopascals, depending on which system we're using. And point 1 is presumably at some higher pressure since it's underwater. So we're going to have a delta pressure. Is there any difference in speed between point 1 and point T? What do we know about the fluid in the standpipe?
It's not moving.
Right. So we're going to treat that entire body of water as stationary, meaning its speed is 0 the whole time. So at point 1, because we can keep in mind, we're not talking about the flowing water. We're just talking about the stationary water. At the border point, the stationary water is staying still. At the top, the stationary water is also staying still. So there's no change in speed because 0 and 0 are the same. Is there any pump or current through resistance in this section of pipe, the standpipe itself? So that means we just have equals 0 on the other side as well. In other words, the standpipe is just a hydrostatic system. We can use the simplified hydrostatic Bernoulli equation where the only things changing are pressure and height. So delta pressure plus rho g delta height equals 0. And then we can fill in some values here. If we treat each one of these as P1 minus PT, or y1 minus yt, the height at the bottom minus the height at the top, then we can fill in some values here. For instance, what's the height at the top? Or what are we calling the height at the top? We've got to set up a coordinate system, right? Yeah, we could call that height plus h. So at this location, we'll say the y value at the top is positive h. And the y value at the bottom, we could call what height?
0.
Yeah, we just call that 0. Alternatively, you could call the top 0 and call the bottom -h. Either way will work, but it would probably be easiest to call the bottom 0 and the top h, because that way, if the height changes, we're just changing the value of h while keeping our 0 point the same. So if we fill those in, y1 is 0, y at the top is +h. And then also, what do we know about pressure at the top?
It's atmospheric pressure.
Right. Pressure of the atmosphere. Note, though, that what we have here is pressure 1 minus pressure of the atmosphere. Pressure at that point minus pressure of the atmosphere is just gauge pressure. So this whole thing is the gauge pressure at point 1. In other words, this term is just telling you how high above one atmosphere that pressure is. And if you wanted to solve for that pressure, how would you isolate P1 here?
You would just subtract the potential energy term to the other side and then add atmospheric pressure.
And since that potential energy term is negative rho GH, that means we're actually adding rho GH to both sides. So we get P1 equals P atmosphere plus rho GH. So if we're talking about absolute pressure, we take 101.3 kilopascals and add rho GH, whatever the height of the fluid is. Or alternatively, in gauge pressure, we would treat P atmosphere as 0. So that means if you treat pressure of the atmosphere as 0, you just get rho GH. So if we want to treat this as a gauge pressure, rho GH is the pressure at point 1. And of course, what that really means is the pressure, the actual absolute pressure at point 1 is rho GH plus 1 atmosphere. But we're treating 1 atmosphere as 0 as if we're talking about gauge pressure. But the important thing there is that if we look at this as a proportionality, specifically as a gauge pressure, the gauge pressure at the bottom is proportional to the height that water reaches at the top. And the constant of proportionality is just density times gravity. So if you can measure the height here, if you know the height, you can take that height and you could just measure that with a ruler, multiply by density of the fluid times gravity on the planet you happen to be living on. And that tells you the pressure at point 1, specifically the gauge pressure. So this standpipe is effectively a pressure gauge. The height that the water is rising to directly tells you what the pressure is. In fact, you don't even necessarily have to measure the height and multiply by rho g. One way you could do this is to mark off tick marks on this column. But instead of marking these as like 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, you could mark these in terms of pressure. You could mark these as like 10 pascals, 20 pascals, 30 pascals, 40 pascals, as long as you measure it right. And then you don't even need to do this calculation. You can just look how high the water rises and read off 50 pascals or whatever, and that tells you the gauge pressure at the bottom. So the standpipe is a very useful way of knowing what the pressure is in the flow pipe underneath. Any other questions on that so far?
On the left-hand side of the board where you wrote that P1 minus atmospheric pressure is equal to gauge pressure, how did you know that P1 was absolute pressure?
It doesn't actually have to be. I mean, this is true regardless. It's just that if you're talking about absolute pressure, P atmosphere is 101.3 kilopascals. If you're talking about gauge pressure, P atmosphere is 0.
Okay, and then for the equation, like on the bottom, how did you know that P1 minus on the other side in black, that first part in the parentheses, how did you know that that was equal to gauge pressure?
This is just how gauge pressure is defined. Gauge pressure is defined as the difference between the pressure at that point versus the pressure of the atmosphere.
Okay, thank you.
Yeah. And you could be using absolute pressure or gauge pressure in any given Bernoulli equation as long as you're consistent about it. And typically what this would be used for, let's say you want to compare 2 locations. Maybe you put in a second standpipe and you find that the water rises up to a lower level. What does that tell you about the pressure at the bottom here? We call that 0.2. What do we know about 0.2 as compared to 0.1? Yeah, it's going to be at less pressure because it has less height of water stacked on top. And if we take a look at this idea that the pressure is rho GH, we could say that P1 is rho GH1 and pressure at 0.2 is rho GH2. These 2 points have different pressures, and we can tell because they're under different depths of water. And then if you want to look at delta pressure, you could say, let's call that P2 minus P1. So that's rho GH2 minus rho GH1. You don't even need to worry about the +1 atmospheres, even if you are using absolute pressure. Because if you did have a +1 atmosphere in each one, what's going to happen when you subtract? If we did put in a +1 atmosphere to this one and a +1 atmosphere to this one, but then we subtract, what's going to happen to those +1 atmospheres? Yeah, those are going to cancel out anyway, right? This is in fact exactly the same as the reason why we don't need to have everything in Kelvin when we're taking a delta temperature. If you're looking at delta temperature, you can just leave everything in Celsius, because to convert from Celsius to Kelvin, you'd have to add 273. But when you subtract to find the delta, all those +273s will cancel out anyway. Exact same thing here. To convert gauge pressure to absolute pressure, you have to add 101.3 kilopascals. But when you're subtracting, all those +101.3 kilopascals will cancel out anyway. So if you're talking about a delta pressure, it does not matter whether you're talking about absolute pressure or gauge pressure, as long as you're consistent. And since gauge pressure is easier to use in this case, gauge pressure is just rho times g times the height, then I would just use gauge pressure for everything in this situation. And by the way, why would we expect a decrease in pressure from 1 to 2? We don't have any change in height because it's a horizontal pipe. We don't have any change in cross-sectional area. So why are we losing pressure from 1 to 2?
Resistance?
Yeah, presumably there's resistance in this pipe. So we're losing pressure in the direction of current. Current is flowing from a high pressure zone towards a low pressure zone. So if we set up a Bernoulli equation from 1 to 2, then we have delta pressure equals negative IR. That delta pressure, P2 minus P1, is just rho GH2 minus rho GH1. So the standpipes tell you about the pressures there. And then if you know the current, maybe you're measuring how much water flows out of the end of the pipe per second, then you can calculate the resistance. And that tells you the resistance of this section of pipe between 0.1 and 0.2. Any questions on that so far? And just as a quick calculation, since rho g is the constant of proportionality, what's probably the most common fluid we would be using here?
Water.
Yeah, water. And what's the most common planet on which we would probably be performing an experiment?
Earth.
Probably Earth. So let's try running the calculation for Earth. Specifically for water on planet Earth. Density of water is 1,000 kilograms per cubic meter. Gravity is formally 9.8. We might round that off to about 10. But that means if we multiply density times gravity, 1,000 times 9.8 would just be 980. And then we end up with kilograms over meters squared, seconds squared. Or you could round that off to about 1,000. And kilograms over a meter squared second squared ends up being the same as pascals per meter. So one way you could do this is you could say that the pressure at the bottom of a standpipe equals 1,000 pascals per meter times the height in meters. So that's the conversion factor. This is a conversion factor that allows you to convert height in a standpipe to pressure. Alternatively, height might be easier to measure in centimeters. So let's say instead of meters, we're talking about centimeters. In that case, we just divide this by 100 and we get 10 pascals per centimeter. So if you just put a ruler on this and that's measured in centimeters, put a mark every centimeter, but instead of labeling them 1 centimeter, 2 centimeters, 3 centimeters, you instead label them 10 pascals, 20 pascals, 30 pascals, you now have a pressure gauge. This is all it takes to make a simple pressure gauge. Take a tube that water can flow up into, put a mark every centimeter, but instead of labeling them in centimeters, mark each of those with 10 pascals, 20 pascals, 30 pascals, etc. And you've got a pressure gauge. Any questions on this whole standpipe thing? All right, then let's get started on electrical circuits. And the whole reason why we introduced fluids first and then electrical circuits right afterwards is that they have almost exactly the same behavior. They're completely different physical phenomena, but they have almost exactly the same behavior in a lot of ways, and therefore they use almost exactly the same equations. And so it's a lot easier to understand electrical circuits if you can think of them as behaving like fluid flow, and you can actually see fluid flow. Electrical circuits, you're not really seeing the electrons whizzing around in the wires, but you can see fluid flowing through pipes. So it's a lot easier to visualize what's going on in an electrical circuit if you can imagine it as acting like a fluid flow. For example, if you have a pipe versus if you have a section of wire. And by the way, on a circuit diagram, we generally just draw wire as a straight line, regardless of what the actual shape is. It doesn't really matter what shape the wire is. All that matters is what it connects to what else. So if you've got a wire on the circuit diagram, that's going to be drawn as just a straight line. And if you see a wire drawn with dots on the endpoints, those dots generally just mean this wire is connected to something else, but we're not going to draw in the rest of the circuit. Presumably this wire is part of some larger circuit, probably forming a complete loop or maybe multiple loops in some complicated arrangement. But if we're just looking at this section of wire, we draw dots on the ends to signify this is connected to other stuff that we're not actually drawing in yet. If we want to compare these, let's say we've got flow happening. In a pipe, what is presumably flowing?
A fluid.
Sorry, what was that?
A fluid or water.
Yeah, we got some sort of fluid. Maybe water, maybe oil, maybe mercury, maybe maple syrup. We got some sort of fluid flowing. And we can talk about current or the volumetric flow rate. And how do we define that? What is our flow rate here? What's actually, or how would we describe how much is flowing?
Area times velocity.
It also happens to equal area times velocity, but that's not how we define it. What is actually changing as this fluid flows? How would we measure how much fluid has flowed? Like if you wanted to describe how much fluid had flows past this point, what measurement are you taking to describe how much fluid?
Is it kilograms per meters per second?
You could describe it in kilograms, but the problem is that depends much more heavily on what type of fluid. Like if you've got oil and water flowing at the same rate, then the water is going to have a lot more mass, a lot more kilograms. Yeah, volume per time is generally how we do this. Volume in terms of just how much space it takes up. So we define current as change in volume divided by change in time. How much fluid, in terms of how much volume of fluid, flows past this point per second. So we might describe the current as like 5 cubic meters per second, or 3 gallons per minute, or 10 liters per hour. Some amount of volume divided by some amount of time, telling you how much fluid in terms of amount of space it takes up per unit of time that we're using to measure it. So this is how we define current in terms of fluid flow. And that's typically going to be measured in meters cubed per second as our standard units of measurement. For electrical flow though, if you've got current flowing through a wire, electrical current is not a fluid. It has often in the past been thought of as a fluid. In fact, if you take a look at textbooks on electricity from like the 1800s, they'll be talking about the electrical fluid. They actually thought it was some sort of weird invisible fluid because it behaves almost exactly the same. But we now know what's actually flowing in a wire, what's actually moving along the wire. Yeah, charge is what's moving. We've got these particles, in this case, electrons that are moving and carrying charge. We don't really care how many electrons though, and we definitely don't care about the volume of the electrons. We care about charge. Charged particles moving. And what's actually happening inside the wire is negatively charged particles, electrons moving in one direction. But we say that the current is flowing in the other direction because we treat current as the flow of positive charge, even though it's negative particles that are actually moving. So the current is going to be defined not in terms of volume, but in terms of charge. Specifically, we would describe it as delta charge over delta time. Instead of measuring how much fluid or how many electrons, how many particles flow past per second, we describe it as how much charge flows past that point per second, the charge being carried by all these charged particles. And we're usually going to write charge as Q. Sometimes capital Q, sometimes lowercase q. I've seen both. And as I understand it, this Q is because this was originally just called electrical quantity. They had no idea what it was, but they knew something was moving around in the wire. So they just called it the electrical quantity. And later they also started calling that charge. But that's just a measure of how much stuff is flowing through the wire, how much electrical, and there's really no other way to describe it. It's just the stuff that flows in a circuit. It's the electrical quantity that we call charge. And of course, we now know that this is tiny particles called electrons moving around in the wires, jumping from atom to atom in the copper. And those electrons have a property that we call charge. But we basically just have to treat charge as some weird undefined substance that is carried by the electrons. Any questions on that so far? And the units of measurement for that, anyone know what charge is typically measured in?
Ampere?
Amperes is the units for current. Amperes.
Oh, would it be voltage?
Volts is something else. Volts is basically
Okay,
the
sorry.
electrical version of pressure. The charge unit, and we're not actually going to use this unit much directly. Mostly we're going to be using other units derived from it. But charge is measured in coulombs, abbreviated as a capital C, as opposed to amperes, abbreviated as a capital A. Most of these units of measurement are named after somebody, and typically the tradition for a unit named after somebody is you don't capitalize the word, but you do capitalize the abbreviation, which is why, for instance, meters and seconds are not capitalized because they're not named after somebody. So amperes is the unit we use for current. And what that means is a charge over a time. Charge is measured in coulombs. Time is measured in seconds. So current is measured, electrical current is measured in coulombs per second, which is abbreviated as amperes. So 1 ampere, or usually just called 1 amp for short. 1 amp means 1 coulomb per second. That is 1 amp of current means that 1 coulomb of charge flows past that point every second. Or if you had like 50 amps of current, that means 50 coulombs of charge flow past that point every second. So that's what current is. Electrical current is describing how much charge, measured in coulombs, flows past that point every unit of time, measured in seconds. And we call that amount of charge, or that amount of current, 1 ampere. 1 ampere means 1 coulomb of charge flows past that point every second of time. Any questions on that so far? And let's take a look at what causes this to flow. This pipe presumably has some resistance. There's some difficulty to flow through, which means what's changing from one side of the pipe to the other? What difference is causing that fluid to flow? The resistance is what's making it difficult to flow. But what's going to be changing? If we were to write out a Bernoulli equation just covering from here to here, we're definitely going to have a negative IR term because there is current flowing through resistance. But yeah, that resistance causes a change in pressure. If you wrote out the Bernoulli equation just from here to here, there's no change in height, no change in cross-sectional area. The only difference is pressure. So that's the delta on the left side of the equation. The right side of the equation is the negative IR term. That accounts for a drop in pressure in the direction current's flowing. Or to put it another way, this negative means current flows from high pressure to low pressure. Current flows in the direction of decreasing energy density. So we would presumably have a high pressure location over here and a low pressure location over here. The current, the fluid current, is flowing from the high pressure zone towards the low pressure zone. Or more generally, from high total energy density towards low total energy density. It's just that in this case, pressure is the only type of energy density we care about. For electrical flow, it's a very similar phenomenon. Fluid flow flows from the high pressure zone towards the low pressure zone. And the more difference in pressure there is, the more current is going to flow. Electrical current flows also from a high zone towards a low zone. But instead of pressure, it's this quantity called voltage. We're going to flow from a high voltage zone to a low voltage zone. Voltage is a new quantity defined in terms of electrical stuff. It also counts as an energy density. Voltage is an energy density. Just like pressure or kinetic energy density or potential energy density. But once again, we don't really want to care about the volume of the electrons. For all the fluid flow stuff, energy density was defined as energy over volume and would be measured in joules per cubic meter, which also turns out to be the same as pascals. For electrical flow, though, we don't want to define energy density as energy per volume because you don't want to have to mess around with trying to measure the volume of an electron. So instead, we measure the energy density as energy over, what would we be using instead of volume here? Instead of talking about volume, what's a good measure of how much electrical stuff? What's our electrical quantity? Charge. So we define energy density for electrical stuff. We define energy density not as energy per unit of volume, but instead as energy per unit of charge. And we call this voltage. It's also sometimes called electrical potential. And note that's not potential energy. Potential energy would be just energy. Energy per unit of charge is called electrical potential. And that's essentially just the formal term for voltage. The formal term is electrical potential. We also nickname it voltage because we measure it in volts as the unit of measurement, we call it. We're going to return to the idea of voltage or potential as energy divided by charge again in 7C when we look at electrical fields. but we're defining it as energy over charge. And you can basically treat this, in terms of wires anyway, you can treat this as like the electrical version of pressure. A difference in pressure causes current to flow through the pipe from the high pressure zone towards the low pressure zone. A difference in voltage causes electrical current to flow through the wire from the high voltage zone towards the low voltage zone. So if we define this as voltage equals energy over charge, energy is usually measured in what units?
Joules.
And charge is measured in?
Coulombs.
So joules per coulomb is the units of voltage, and we abbreviate this as volts. So 1 volt means 1 joule per coulomb. And also 1 ampere, the unit of current, equals 1 coulomb per second. And we actually get a very interesting result if we combine these. If you multiply amps times volts, if we actually replace those with their base units, coulombs per second, and then volts can be replaced with joules per coulomb. Coulombs per second is amps, or joules per coulomb is volts. What happens when you multiply those together? Yeah, the coulombs cancel out and we get joules per second. Anybody remember from 7A what joules per second is called? Yeah, that is watts, the unit of power. Power means energy per time in the sense of how much energy is being delivered or created or used up or whatever per second. So if you multiply amps times volts, if you multiply current times voltage, you end up with a measurement of power. In other words, if you know how much current is flowing in this wire and you know how much the difference in voltage is, you can just multiply those together to calculate how much power is being produced or how much power is being used up. So power equals current times voltage. And since power is described as how quickly energy is being produced or used up or transferred, this is very useful, for instance, for light bulbs. For a light bulb, the light bulb is giving off energy as light and heat. If you calculate the power of the light bulb by multiplying current times voltage, that tells you how bright it is. And it's not entirely how bright it is because it's giving off energy as both light and heat. So some of the energy it gives off is light, some of the energy it gives off is heat. But power gives you a good approximation of how bright it's going to be. If you want to compare the brightness of 2 light bulbs, you can calculate the power for each one, current times voltage. And whichever one has a larger power is going to be brighter and hotter also. It's going to be giving off more heat as well. Any questions on all these units of measurement so far? Yeah, I really like going into more detail on the units. It often gets skimmed over. I think a lot of the professors just assume everybody already knows about units. But I think it's a lot easier to understand what's going on if you actually keep track of the units and know what's actually being measured. Any other questions on that so far? Oh, and by the way, for that exact reason, I also included a lot of information on the units in that, that reference sheet I mentioned. If you go to math.ncheese.org/P7B, there should be a units reference sheet if you scroll further down. Just click on the link to, or not just units, but electrical reference sheet in general. So you might find that useful for studying from as well. And let's take a look at one more quantity while we're at it. Because the pipe was having current flow because there's a difference in pressure. And those quantities are related by this equation. You get faster current flowing, the more pressure difference there is. But there's also this constant of proportionality called resistance. We can set up almost exactly the same equation for the wire. We just have to modify what the variables are describing. We still have current flowing because there's a difference in voltage. And by the way, if these were the same voltage, I wouldn't expect any current to flow. The current flows because there's a difference in voltage. the current is flowing in the direction of decreasing voltage from high voltage to low voltage. So we're going to have a negative sign for the exact same reason. And there's going to be a constant of proportionality, which we also call resistance. So this resistance is a property of the wire itself. And typically, most wires have very little resistance. In fact, they have such low resistance, we round it off to 0. And this is why we use materials like copper or other metals for wire. You want to use a metal for a wire that has as little resistance as possible. In fact, if you want to have something that does have resistance, typically that's some device that turns the electrical energy into something else. Like a light bulb, for instance, is turning the electrical energy into light and heat. A motor turns the electrical energy into kinetic energy and heat. A buzzer turns the electrical energy into sound energy leaving the system and heat. Usually something that we just call a resistor with no other detail is just turning the electrical energy into heat. But we typically mark that as a sort of a zigzag shape in the wire. So a wire with a zigzag in it is the way we draw a resistor. That doesn't mean the wire actually is shaped like this. This is just the symbol we use in circuit diagrams for a generic resistor. That includes light bulbs. If we're specifically talking about a light bulb, though, we often draw it like this. And that doesn't mean it's not a resistor. A light bulb is just one type of resistor. So this zigzag means resistors in general. If it's a light bulb specifically, we often draw it like this, but it still counts as a resistor. It still follows this behavior. And this is supposed to look like a glass bulb with a little filament inside. So it's a stylized depiction of a light bulb. But in general, resistors are always going to follow this property, usually called Ohm's law. Ohm's law is just saying what we already talked about for fluid flow in the Bernoulli equation. It's just this very specific difference in voltage from one side of the resistor to the other equals opposite of current times resistance. Current being how much charge is flowing per second, voltage being the energy density in terms of energy per unit of charge, and then R, the resistance, is describing how difficult it is for current to flow. And if we take a look at those units of measurements, what are we measuring voltage in?
Energy per coulombs.
Yeah, that's joules per coulomb, although we can just abbreviate that as volts. And what about current? What do we call the units of measurement for current? Yeah, that's amps, or amperes if you want to say the whole term, which we could also describe as coulombs per second if we need to. And in order for these to match up, what has to go here? What do we have to be measuring resistance in to make this work out? Ideally, we want to get rid of amps and turn it into volts, right? So what could you put in the numerator and denominator to get rid of amps and turn it into volts? It's going to be related to power, but not quite the same thing in this case, because power was what we got if we multiplied volts times amps. But here we want to cancel out amps. So where should we put amps in this fraction? If you want to cancel out amps, all we need to do is put amps in the denominator. That way amps and amps will cancel out. And we want to introduce volts, so we can just put volts in the numerator. You can use this, by the way, to turn any variable or unit into any other variable or unit. If you have a variable and you want to turn it into another variable, just multiply by a fraction variable you want over a variable you want to cancel out. So the units for resistance are going to be volts per amp, and we also call that ohms, named after the same guy that Ohm's law is named after. Ohms means volts per amp. And ohms is abbreviated as the Greek letter capital omega. So that's the unit for resistance. Resistance is measured in ohms. Typically, if you look at a resistor, it'll be labeled in terms of like 3 ohms or 5 milliohms or 2 centiohms or something. Usually they're going to be labeled in ohms or milliohms. 1 ohm is a fairly large amount of resistance. So a lot of resistors are much, much smaller than that. But that's our stock unit of resistance. Resistance is measured in ohms, and ohms times amps is volts. You could also write that ohms in terms of all this other stuff. We need to cancel out coulombs and introduce another coulombs in the denominator, so we'll need coulombs squared. We got to get rid of seconds and introduce joules. So another way of writing ohms is joules seconds over coulombs squared, but usually it would just be written as volts over amps, because typically volts and amps are what we're actually combining it with. That means anytime you see ohms, you can replace it with volts over amps, and vice versa. Anytime you see volts over amps, you can replace it with ohms. There are just different ways of writing exactly the same thing. Any other questions on that so far? So we've got volts, amps, coulombs, ohms, and also power. Watts is usually thought of as an electrical unit, but it's not actually an electrical unit. Watts is just a unit about energy and time. It's used often in terms of electrical circuits, but keep in mind, power is more universal. Power is about any situation involving transfer of energy from one place to another as time passes. All these other ones, volts, amps, and ohms, these are all specific to electrical circuits only. So we're out of time for now, but we'll take a look at more about how to apply these units and formulas like Ohm's law next time in some actual examples. In the meantime, take a look at the reference sheet I've got on math.ncheese.org/P7B, and make sure you're familiar with all these units of measurement, all these quantities, how they're defined, and most importantly, how they're related to each other. Feel free to email me or contact me online if you have any other questions, and I will see you next time. You're welcome.